Hi, this video is on acids and bases. We've learned a little bit about acids and bases, but now we're going to build on what we already know. Well, first of all, the first person who really seemed to define an acid was a Swedish scientist by the name of Arrhenius. That was his last name. He said that acids, when you put them in water, will increase the H+ concentration. Remember, we call H+ protons. So, in other words, HCl could be our good example. If we put it in water, it would come apart into the H+ ion and the chloride ion. And so, this is showing that the acid dissociates in water. And another word for that is that this acid in water will ionize in water. So, it produces ions when you put it in water. And acids make the H+ ion. He defined bases as something when you put them in water, they increase the hydroxide ion concentration. So sodium hydroxide, when you put it in water, would give you sodium ions and hydroxide ions. And so that was the definition of acids and bases. But it wasn't quite enough because they were finding that some salts, like say sodium carbonate, when you put it in water was basic. But there was no obvious hydroxide ion in the formula for sodium carbonate. So two other scientists by the name of Bronsted and Lowry, and so this is the Bronsted-Lowry definition of acids and bases. And they defined a Bronsted acid as a proton donor. Okay, so you got to have that H+. And the Bronsted base is a proton acceptor. And so if something is donating something, something has to be taking it. And so this base is basically taking the proton that the acid is donating. And then, well, what do you call an acid after it gives away its proton? Well, after an acid gives away its proton, it's called a conjugate base. Okay, so this is what is formed after an acid donates its proton. And what do you call a base after it accepts a proton? Well, now it's turned into an acid, and we call it a conjugate acid. And that is what is formed after a base accepts a proton. Okay, so this is what happened with the carbonate that I referred to. Now see, that doesn't look like a base from the Arrhenius definition because there's no OH there. But when you put carbonate in water, what happens is the H from the water is transferred over here and we form bicarbonate, and like Arrhenius said, we are forming hydroxide ions in solution. So anyway, there are two definitions of acids and bases. There's the Arrhenius definition and then the Bronsted-Lowry definition. Well, let's go on and talk about the Bronsted-Lowry definition and conjugates. All right. NH3 is reacting with HF. One of these is going to act like the acid and donate an H+, and the other one is going to accept the H+. Well, here we have HF, and over here we just have F-. Oh, this donated the H, so this is the acid. What does an acid form after it donates its proton? It forms the conjugate base. So you take away a proton from an acid and you get a conjugate base. Now this is looking like a base because it's negative, which means, yeah, it could accept an H+. Well, that must make the ammonia here, the NH3, the base. We can't have an acid without a base. If it's donating its proton, it has to give it to something. And so on this reactant side, we're going to have an acid and a base. And so here is our base. After that base accepts the proton, so remember, we're transferring an H and a plus. So instead of having 3 H's, we now have 4 H's, and now we have a plus sign. And this now becomes the conjugate acid. And this should look like an acid to you, even though that H isn't out front. We've got an H and a plus sign here, so this ammonium ion is acidic. So every Bronsted acid has a conjugate base, just to remove the proton. Every Bronsted base has a conjugate acid. You just need to add an H and a plus, okay? So every Bronsted acid has a conjugate base, and that conjugate base is formed after you remove the proton. Every Bronsted base has a conjugate acid. You just add the H and the plus. Okay, so let's try this again. This is the cyanide ion and water. Oh my goodness, the cyanide gained a proton. It was a proton acceptor. That means it acted like a base. So therefore, water must be the acid. Did it indeed give away an H plus? It did, and it formed the OH ion over here, the hydroxide ion. All right, so if cyanide is the base, this has got to be the conjugate acid. And the hydroxide, well, yeah, that's a base. And that is the conjugate base formed from water. So the water here was acting like an acid. It was donating its proton. All right, so let's try some more. Identify the conjugate acid base in the following reaction. Phosphoric acid in water. All right. Oh, the phosphoric acid donated its proton, so that's the acid. And here, look what the water's doing. This time, it's acting like a base. So, remove an H and a plus, and you get H2PO4 with a -1 charge. That's our conjugate base. And after water acting like a base accepts that proton, it forms a hydronium ion, and that is the conjugate acid of water. Okay, now we just saw water act as an acid in one slide, and then it acted like a base in another slide. So there are some things that can act like an acid or a base, and they're called amphoteric. They don't really make a commitment. It's like it depends on who they're around. If they're around a base, they'll act like an acid. If they're around an acid, they'll act like a base. So water is something that can act like an acid or a base. It can either accept or donate a proton. Here's something else, bisulfite. That negative charge makes it look like it could accept an H plus, and also this H out front looks like it could donate an H, and it can do either one in water. So it is amphoteric. Here we have it acting like the proton donor. So it's giving an H plus to the water, forming the hydronium ion, and leaving behind the sulfate ion. So here, this is the acid. The water is accepting the proton. It's the base. The sulfite ion is our conjugate base, and the hydronium ion is the conjugate acid. But look down here, the hydrogen sulfite ion is acting like the base because it's taking the proton from water. And so water here is acting like the acid, and then this becomes the conjugate acid, and this becomes the conjugate base. Okay, you know, water we saw could act like an acid or a base. When water is with an acid, it acts like the base. So look here, this proton comes off of the acid. So here's our acid. Water is acting like the base. And it forms a chloride ion, which is the conjugate base. And that hydronium ion, the conjugate acid. All right, let's go ahead and look at acetic acid in water. Okay, here, water is going to act like the base. Acetic acid is going to be our acid, and it will donate a proton, and we'll get the hydronium ions, and we're going to get the acetate ion. Now this is a weak acid, which means that it doesn't completely dissociate in water. It only forms a few ions. And we're going to look at equilibrium, which means the reaction goes both ways, and that's in our next unit. But weak acids are ones that do not completely ionize. do not completely break apart. They do make ions in solution, but just not, the amount of ions that a strong acid would make in water. Okay, here we've got an example of water acting as an acid and donating its hydrogen to ammonia, which is our base. Water is acting as the acid. The ammonium ion is the conjugate acid, and the hydroxide is the conjugate base. And again, this is a weak base. See how I have the double arrowhead here? Not every ammonia molecule pulls a proton off of water. So this is an equilibrium, and we're going to talk about that in the next unit. Just know that weak acids and weak bases don't completely ionize. Only a few of the ammonia molecules will do this in solution. Okay, now this is kind of weird. It's called the auto-ionization of water. And it's where water acts as an acid and a base with itself. So one water molecule donates a proton, so we'll call this one the acid. We'll call this one the base. And again, see, this is at equilibrium, okay? It doesn't go to completion, and we get some hydronium ions and some hydroxide ions in solution. Okay, well, we are going to stop with this, and then in our next video, we're going to talk about different acid-base reactions. All right, have a good day.